As you can now see, I'll be talking about a background-independent algebra in quantum gravity. So, in ordinary quantum mechanics, we usually consider the observer to be outside the system that's being observed. But that's problematical in the presence of gravity, most obviously in the case of a closed universe. No one can look at a closed universe from outside. Remember, in gravity, you don't know what the space-time is. The space-time evolves on its own. So somebody outside the universe has no idea what the universe is, and certainly can't look at it from outside. So in gravity, we have to think of the observer as being part of the system. That's less so in an asymptotically flat spacetime, or asymptotically ADS. Then you can have an observer at spatial infinity who's effectively looking at an observer, the universe from the outside. But in general, and most obviously in a closed universe, such as we may be living in, no one can look at spacetime from outside. Now, in ordinary quantum field theory, you can pick an arbitrary region U in spacetime and define an algebra of observables in that region. So schematically, I've drawn a general spacetime M and an arbitrary region U in it, which I took to be a causal diamond of some kind. But there are problems with this in the presence of gravity. Well, one immediate problem is that since space-time is fluctuating, it doesn't make sense in general to draw an arbitrary diamond on the map and say that's our region. It has to be a region that can be defined in some invariant way. For example, the exterior of a black hole horizon. But more fundamentally, why do we want to define an algebra unless it's the algebra of observables that somebody can measure? So in ordinary spacetime, we can pick an arbitrary region on the map, and we imagine someone living outside the spacetime and manipulating it at will, but only in that region, for example, or we could put additional conditions. In ordinary quantum field theory, we can do all kinds of things arbitrarily. But in gravity, it doesn't seem to make much sense to consider an algebra unless it's the algebra of observables available to someone. We could put some technological limits on the observer's capability and consider all operators that are measurable with those technological limits. Or we could simply make an idealization and ignore technological limits. But anything that's worth defining should be an algebra of observables accessible to someone in the spacetime. So I want to construct an algebra that describes the measurements made by an observer. I'll assume the observer knows the laws of nature, but has no knowledge of the state of the universe except whatever is gleaned from observation. That doesn't match us perfectly, since our knowledge of the laws of nature is incomplete. So the second part fits where we are. We know nothing about the state of the universe except what we observe. But the first part doesn't, because we've been using our observations to learn the laws of nature as well as the state of the universe. I consider the idealization of an observer who knows the laws of nature because it's harder to construct a model of an observer who's trying to learn them. So the algebra will depend on the laws of nature, but it's required to be universal and background independent, meaning that it's defined once and for all with no knowledge of the specific spacetime in which the observer is living. And then different spacetimes will end up giving different representations of the same algebra. So here I've listed some background papers, but I won't explain what's in them. The only thing I'll say is that the paper marked with a star is the most immediate background to what I'll be saying. So what I'll be doing actually is to rethinking the construction in that paper from a different point of view. Now, one thing I'm often asked about is we expect that in a full theory of quantum gravity, an observer cannot be introduced from outside, but must be described by the theory. Is it useful or important to take this into account? Well, first of all, what does it mean to discuss an algebra that's contingent on the presence of an observer? What it means is that we define an algebra that makes sense in a subspace of states in which an observer is present. We don't try to define an algebra that makes sense in all states for two reasons. One, we can't, and two, if we could, it wouldn't mean anything. So sometimes people are unhappy with the very schematic way that I'll model the observer. So a question you could ask is, since the observer is made from the laws of nature, would it be useful to model the observer more realistically using the laws of nature? Well, let's consider us as examples of observers. We can be modeled using the standard model of particle physics. But I claim that that's not useful in understanding, in modeling our explorations of cosmology. What is important is to model not how we're built out of the standard model, but what are our capabilities. So therefore, I will make no attempt to model the observer microscopically, which with us as examples of observers I claim is not useful. And instead, I will only discuss what the observer can measure. First, let's describe the situation in the absence of gravity. The observer propagates in space-time on a geodesic gamma. The world line is parameterized by proper time of the observer. As in, well, classic work of Unruh, but also in many other papers, the observer measures along gamma, for example, a scalar field phi, or the electromagnetic field F mu nu, or the Riemann tensor, R mu nu alpha beta, and also their covariant derivatives in normal directions. I don't have to mention the covariant derivatives in tangential directions because I'm already including these fields at all tau. So their time derivatives, their tau derivatives would add nothing, but we do have to include their normal derivatives, which are additional local fields along the world line. So there's a preliminary point, and I wasn't sure whether to explain it or not in this lecture. I decided to spend a couple minutes to explain it. I hope that won't distract too much from the main thing I want to get to. But a preliminary point is you could ask whether idealizing the observer by a world line is too much of an idealization. Can you actually define an algebra of observables along a world line? The answer is yes, but the point isn't completely trivial, so I want to explain it. An elementary but not so well-known point is that smearing a local field, such as phi or any other, along a Timelike curve is indeed sufficient to obtain a densely defined, although unbounded operator, to define a true operator. I want to explain that statement. So because of that statement, there does rigorously exist an algebra of operators defined by smearing along a Timelike world line. By contrast, smearing in space is not effective at defining an operator, except in special cases where phi has very low dimension. An important special case is that it's not possible to define an operator by smearing a local field on a cut of a black hole or cosmological horizon. If that was possible, black hole and cosmological, well, the physics of horizons would be completely different if you could define an operator by smearing on a horizon cut. Such operators would be central, but you can't, for reasons you'll see in a moment. Well, first of all, why do we have to smear in the first place? If omega is a Hilbert space state, the vacuum or any other, and 5x is a local operator, then 5x acting on omega is never a Hilbert space state, because its norm, which would be given by this expression, is infinite. You see, the norm is the two-point function evaluated at x equals y, and it's infinite because of short distance singularities. So what we informally call a local operator is never a Hilbert space operator. It maps any Hilbert space state out of Hilbert space. How do we make Hilbert space operators? Well, let's try smearing in space. So I'll try to smear in d spatial dimensions, where in 4 dimensions, d is 2 if you're trying to smear on a horizon cut, or d is 3 if you try to smear in all of space-time. And d is actually 4 if you try to smear in Euclidean space, because Euclidean space would be like treating time as another space coordinate. So different values of d are interesting. So we smear in space. We take a smooth function of compact support in space, and we define phi sub f as the integral of phi times a smearing function. And then we see whether, we want to know whether phi of f acting on the vacuum is a Hilbert space state or not. So we compute its norm squared, which is this, and it's given by this integral. And to decide whether that integral converges, which would mean the state is normalizable, we need to know how severe is the short distance singularity in the two-point function. So I'll assume that the short distance, well, normally in quantum field theory, short distance singularities are power laws. So that could be because of conformal invariance, but it doesn't have to be. But anyway, I assume that the short distance singularity is a power law, or maybe up to logarithms or something, which wouldn't be important, plus less singular terms. And then, given this nature of the singularity, you see this integral converges if and only if 2 delta is less than d. So, for example, QCD is a theory where we can't satisfy that condition. The smallest value of delta in QCD is 3 for the operator Q bar Q, where Q is a quark field. And even if we take little d to be 4, because we tried to smear in Euclidean space, we failed to define an operator in QCD by smearing in space. So space doesn't work, but time does. Smearing in time gives a true operator regardless of the value of delta, as was first proved by Borchards in 1964 in a paper that is amazingly obscure, as far as I can see. So it's very important to take account of the Feynman I epsilon. So I've written the 2-point function again, but now for operators at the same point in space but different times. So the 2-point function in time has the same singularity, same power law, but the Feynman I epsilon is crucial, so I've included it. The Feynman I epsilon didn't help us when we went in a spatial direction, but it does help us in time. So now we do the same thing again. We smear phi at a given point in x. We smear it only in time using a smooth function of compact support. And now we compute the norm of the state. Well, I've only written the most singular term in the operator product expansion. There are less singular terms, but they're bounded by less singular powers of t minus t prime minus I epsilon, and they all have the same I epsilon. So the less singular terms would be treated the same way I'll treat the leading term. So the norm of the state is given by this integral. And it's obviously a finite integral if epsilon is positive, but the question is what happens as epsilon goes to 0? And I claim this integral has a finite limit as epsilon goes to 0. To prove that, we just write t minus t prime minus I epsilon to a negative power as a derivative of something with less negative power, and with a suitable constant Cn. And then, therefore, the formula for the norm, well, I just substitute for this in terms of this, so I've written it here. Then we integrate by parts n times, and there are no surface terms because f had compact support, and so we get this formula for the norm. And such a formula holds for every n, and obviously for sufficiently large n, this is finite. Oh, I wrote as n goes to 0. I meant, of course, as epsilon goes to 0. So it's possible to define an algebra of operators smeared along a time-like worldline. But what is this algebra? So this question is answered by the time-like tube theorem that goes back to another surprisingly little-known paper of Borchards, even earlier, actually. And modern proofs are all, however, all based on the work of Araki a little later, rather than Borchards' original proof.
Sorry, why did you think of the derivatives do not work for the spatial?
Because there's no epsilon. Well, okay. The epsilon meant that we had a well-defined integral before we took the limit. And then we try to take the limit. When we have a well-defined integral, we can integrate by parts. In space, we didn't have a well-defined integral, so we didn't have anything to try to do. So what we were supposed to learn from that was that idealizing the observer by a world line isn't too crude. We can still rigorously define an algebra. But if we want to know what that algebra is, we need the time-like tube theorem, which you can roughly think of as a rigorous version of HKLL reconstruction, perturbatively. But the time-like tube theorem is really a non-perturbative theorem. So the time-like tube theorem says that the algebra of operators along a time-like world line is equivalent to the algebra of operators in a certain open set E of gamma called a time-like envelope. It consists of all points that you can reach by deforming gamma through time-like world lines. So in a simple case, if I consider the blue thing, which is a portion of a time-like world line, E of gamma is the causal diamond defined by those 2 points. In general, there are subtleties about exactly what E of gamma is, which I won't go into. So the Timelike tube theorem holds for finite segments of Timelike world lines, and actually for more general sets that I won't need today. Although ultimately I will consider a complete Timelike world line. So what we learned from the Timelike tube theorem is that in the absence of gravity, the algebra of operators along a Timelike geodesic, or any Timelike world line really, is equivalent to the algebra of operators in a certain open set. So in ordinary quantum field theory, we would define an algebra for an arbitrary open set. We can't really do that in gravity, but what we can do, not only we can do it, but it seems physically motivated, is to define an algebra of operators accessible to an observer on some world line. And that is actually, in the absence of gravity, would be the algebra of region. So it seems like a substitute for the algebra of region that's better defined in the presence of gravity and makes more sense with gravity included. Now, to understand more concretely what is this algebra in the presence of gravity, let's focus on a particular observable. Yes?
Are we also wanting to assume that the observer can store and process all the
We do want to, yes. But I won't, that would be a more realistic model. But I won't, and if an even more realistic model might put bounds on the information processing. But I won't do that. That would require more sophistication than the model I have. The model I have will, well, okay. I'll say later exactly what we have. But Andy is asking if we should somehow model the observer's ability to store and process information, and that would, as I said before, the microscopic details of our biology, modeling it by the standard model, aren't useful, but a better model of our capabilities might be useful or important. So in the absence of gravity, for example, we have a scalar field phi that we measure at x of tau, where x of tau is the observer's position at proper time tau. I'll just abbreviate that as phi of tau. When we take gravity to be dynamical, there's a very important point that might seem minor at first, but it actually changes the picture significantly. There's no natural zero of proper time. Between two events on the world line, the elapsed proper time is well defined. But there's no natural absolute zero of proper time. So we have to take into account that the same world line can be embedded in a given spacetime in different ways, differing by tau going to tau plus a constant. I don't consider other diffeomorphisms of the world line because I assume the observer has a mass and a natural proper time along the world line. But we can't avoid the fact that there are shifts of the proper time by a constant that are symmetries. So we have this world line that's embedded in space-time. The observer, to begin with, doesn't know what is the space-time in which it's embedded, but the same world line could be embedded in the same space-time in different ways, differing by a shift of tau by a constant. So phi of tau by itself isn't a meaningful observable when we take this into account. We need to introduce the observer's degrees of freedom and define tau relative to the observer's clock. In a minimal model, we equip the observer with a Hamiltonian mc squared plus q. M is the observer rest mass, and q is the energy of the clock, and the canonical variable minus I d by dq. But it turns out that it's better to assume the observer energy is bounded below, which makes m into the observer rest mass. Well, we will.
Are you going to give us comments on what happens if that's not the case?
Well, only it's a deficiency of my presentation, and I don't know a nice way to make a discussion for an observer whose world line is not infinite in the past and future. I was going to acknowledge that later, but you've brought it out right now. Yes? No, I'm not sure if you were here about 8 minutes ago, but as I said, the observer is modeled by the observer. We're defining an algebra that makes sense in a subspace of states in which the observer is present. We're not trying to microscopically model the observer in the theory. For example, if we are the observers, we could be modeled by the standard model, but trying to do that doesn't seem to be helpful in discussing how we understand cosmology. As I said,
say that, but I maybe didn't understand the implication. So maybe this is related to Bob's question. Realistically, as the observer, even if once it's part of the system, you interact with the system, it becomes difficult to say what part of the system you would actually define as the observer.
No, the observer can indeed interact with the system. The statement that the observer can measure the operators along the world line has built into it the fact that we allow a completely general interaction of the observer with the system, but only localized on the world line.
But if I model the observer as an elementary particle, for example, it might annihilate with another particle and be created as a new particle. I'm confused how we draw the boundary between such microscopic things where it becomes impossible to identify against the system that we call the observer.
Well, to the extent it makes sense to discuss observations in cosmology, there is such a distinction. Modeling the observer as an elementary particle is too crude, I'm sorry to tell you. I think that my discussion is actually a much more realistic model. I'm not fully taking into account, I'm not modeling exactly an observer with the world line and measuring arbitrary quantum fields along the world line. It's much closer to what we mean by it's much closer to a description of us than a model in which the observer is an elementary particle. It's true that my discussion will not take into account space-time singularities, but I think we're also getting questions that could be postponed a little bit.
Okay.
Because despite the fact that arguably I sinned by jumping ahead and answering one question. So it's better to assume the observer energy is bounded below, say by Q non-negative. But then we should only allow operators that preserve this condition. So for example, we don't allow the operator e to the minus ip, which does not preserve the condition that Q is positive. We replace it by pi e to the minus ip pi, where pi equals theta of Q is the projection operator on non-negative Q. So all operators that I write will be projected before and after onto Q and positive Q. Something I do want to say, since some of you asked about being more realistic, is that we could put an upper bound on the observer energy. I think no one is surprised that it's physically motivated to put a lower bound on the observer energy. Otherwise, the observer could have negative energy, which would be unphysical. So giving a positive rest mass to the observer, a positive lower bound, probably doesn't surprise anyone, and it makes the math work better, as you'll see in a bit. Putting an upper bound on the observer energy isn't actually important for anything I'll tell you today, but it makes the model more realistic, because the upper bound would give the upper bound on the energy that the observer has to power any experiment. And that would turn out to map into a lower bound on the resolution, the time resolution you could achieve in any measurement. So that's a simple example of an improvement of the model, to put an upper bound on the observer energy. Yes?
So the procedure you do for setting Q positive,
Yes.
with this projection, like, would it be equivalent if you just started with a Q square or something? Because it seems
Well, taking Q squared also seems slightly arbitrary, because for each value of Q squared, there are two values of Q. So that would be like equipping the observer with an extra qubit. So we might want to equip the observer with many extra qubits to account for the details of how measurements are made and information is stored. But I don't think we'd gain much by adding one extra qubit. So now, so remember, the point was that, in gravity, we have to put constraint operators that the state is invariant under diffeomorphisms. So first, we could impose all the constraint operators away from the observer world line. Let's assume that's already been done. Secondly, since there's a preferred notion of elapsed proper time along the world line, the only important diffeomorphism, we can partially gauge fixed to where the metric is constant along the world line. And then the important diffeomorphism that remains is a constant shift of the observer's time. So the important constraint that remains is the sum of the observer Hamiltonian that moves the observer degrees of freedom forward in time, plus a bulk constraint operator that moves the world line forward in time. There's no canonical choice in general of that constraint operator. It doesn't matter which one we choose, because all the diffeomorphisms away from the world line have already been imposed. In other words, I first define a Hamiltonian, which is Hilbert space that's too big, where I ignore the fact that there's no zero of the observer's proper time. Impose all the constraints under that assumption. There's one more constraint to impose, which is the sum of the observer Hamiltonian H and a bulk operator, where the bulk operator is a gravitational constraint operator that generates a shift of tau along the world line. So an operator that commutes with H hat is invariant under a space-time diffeomorphism that moves the observer world line forward in time, together with the time translation of the observer system. Well, how do we find operators that commute with H hat? Since the bulk constraint operator, by hypothesis, commuted with phi of tau, where phi is any operator along the world line, is minus I phi dot. And since the observer Hamiltonian is a C number plus Q, we need to have Q with phi equals plus I phi dot. And we can achieve that just by setting tau equals P, the conjugate of Q, so that Q is ID by dP. Or equivalently, more generally, tau could be P plus S for a constant S. So a typical allowed operator is phi evaluated at P, the conjugate of Q, an operator which roughly corresponds to the observer's proper time, or phi P plus S, except we need to remember these projection operators, pi. So these are typical allowed operators. In addition to these operators with phi possibly replaced by the electromagnetic field or the Riemann tensor or something else, there's one more obvious operator that commutes with H hat, namely Q itself. So we define an observer algebra that's generated by the phi hat S as well as Q. Now, it hopefully sounds like this is background independent, because we defined it without picking a background. We didn't say anything about the space-time the observer was living in. But background independence really depends on interpreting the formulas properly. We won't get background independence if we think that the symbols I've written are Hilbert space operators. That's because to have a Hilbert space in which these things act, we have to pick a space-time M in which the observer is propagating and a world line in which the observer lives. And then we won't have background independence. To get background independence, we have to think of the observer algebra as an operator product algebra rather than an algebra of Hilbert space operators. Then the algebras for different M's are inequivalent representations of the same underlying operator product algebra. In the absence of gravity, we would characterize the objects 5 tau by their universal short distance singularities. That characterization requires no knowledge about the quantum state. For example, Holland and Wald were treating a somewhat similar problem. They wanted to explain what it means to define the same quantum field theory in different spacetimes. If you think about it a bit, that's not completely trivial. If you talk about Hilbert spaces and operators in Hilbert space, you'll have trouble. But if you formulate the quantum field theory in terms of universal operator product relations, then you can indeed characterize a quantum field theory in a way that's independent of the spacetime, provided you allow the coefficients in the operator product expansion to depend on the Riemann tensor and its covariant derivatives. So that was, in their work, that was a framework to explain what it means to have the same quantum field theory in different spacetimes. I'm doing something very similar, except that I'm trying to explain what it means to have the same observer algebra in different spacetimes. And to do that, we characterize the observer algebra by short distance, by OPE singularities, except for a correction I'll make in a second. Because I often run into confusion, I want to remark that an operator product algebra is not an example of an algebra. Not in an interesting way, at least. There are no non-trivial relations in the usual sense of an algebra where you say that A times B equals C. You don't have anything like A times B equals C. Rather, A times B is asymptotic to C as tau goes to tau prime. In an algebra, you don't say anything like that. So Except in a stupid sense, an operator product algebra isn't an algebra. It's defined by short distance expansion. It's just a different kind of thing. I wish there was a non-confusing name, but I don't know one. Mathematicians use the phrase factorization algebra, but that raises the same confusion. Now, okay, I stated what I meant there by an operator product algebra in the absence of gravity. In the presence of gravity, and including the observer and the constraint, the short distance expansion in powers of tau minus tau prime actually becomes an expansion in powers of q, 1 over q. What did I do? If we characterize the observer algebra by an expansion of operator products in 1 over q, then in that sense, the observer algebra is background independent. But it's not an algebra in the sense that you're accustomed to from algebra. Or if you want to call it one, it's a rather stupid one, in which there are no relations. The interesting properties are the short distance or large q expansion. Now, there's a very special case that turns out to be important. That's the case that M is an empty de Sitter space with some positive value of the effective cosmological constant. So I've drawn the Penrose diagram with the far future at the top and the infinite past at the bottom. And coordinates can be chosen so that well, first of all, de Sitter space is a homogeneous space, so any two geodesics are equivalent by the symmetries. So it doesn't matter which geodesic we pick. Having picked a geodesic as the observer world line, we can pick coordinates in the Penrose diagram so that the observer world line is the left edge as drawn. And then the region I've drawn in green is the region to the past of the future horizon and to the future of the past horizon of the observer. It's the region causally accessible to the observer. And in a background de Sitter space, as opposed to quantum gravity, which is fluctuating around de Sitter space, the Timelike tube theorem would tell us that the algebra of observables along the observer's world line is the same as the algebra in the green patch. The green region is called a static patch because it's invariant under a particular de Sitter generator H that advances the observer's proper time. In the absence of gravity, there is a distinguished de Sitter invariant state, which I'll call psi ds, such that correlation functions in this state are thermal at the de Sitter temperature. The de Sitter temperature is sort of 1 over 2 pi times the radius of curvature of the spacetime. And the thermal nature is usually understood by the fact that under analytic continuation to imaginary time, the observer world line becomes a great circle in a sphere. And the inverse temperature is simply the circumference of the circle. I'll assume, though, that most of you are familiar with the thermal nature of correlations in de Sitter space. A precise statement of that thermal nature is that, well, I'll state it just for 2-point functions. Of course, we could state it for n-point functions. 2-point functions have 2 key properties. One is simply time translation symmetry, that you can shift the times of both operators by a constant. The second property, but this is, of course, not thermality. This is much more general. This is just the statement that the static patch is static. The statement that the static patch, that observables in the static patch are thermal means the following. Operators in quantum mechanics don't commute. So the expectation of a product of 2 operators in the state psi ds isn't the same as the same product in a different order. But thermality means that if you shift, thermality means roughly if you shift the proper time of one operator by minus I beta, where beta is this thing, then you can exchange the 2 operators. That's an informal statement. A precise statement involves talking about holomorphy in a strip and boundary values at the 2 ends of the strip. Now, including gravity and the observer, well, first of all, when we include gravity, linearized gravitons in de Sitter space would similarly have a state psi ds. So we extend the notion of the state psi ds to include gravity, but now we include the observer, and we give the observer energy a thermal distribution at the de Sitter temperature. So that means that to make the probability distribution of the observer e to the minus beta q, I take the wave function to be e to the minus beta q over 2 with the normalizing factor, the square root of beta. So we define a state that I'll call psi max, which is psi de Sitter times this normalized exponential. And then we replace the operators along the gravitational world line by gravitationally addressed versions of themselves, which are these. So we replace the state psi ds by the state psi max, and we replace operators phi along the world line by these things. Then a straightforward computation, no fancy math required, only a little, you have to do a couple integrals and deform a contour in the complex plane. A straightforward computation shows two facts. One is we still have time translation symmetry, but what's shifted by time translation symmetry is this parameter s, the offset in the proper time of a particular operator. So the two-point function only depends on the difference, s minus s prime, not on s and s prime separately. And second, the KMS condition simplifies. It no longer involves a shift in imaginary time. So now it actually is true that the expectation value, not in the state psi ds, but in the state psi max, of a product of two operators is independent of their ordering. That's the key point, actually. And I'm not doing the computation for you, although maybe I should have planned on doing it. I promise you it's a short elementary computation with no operator theory required. So this condition tells us that if we define a function that, if we define the expectation of an operator A in the state psi max to be what I'll call trace A, that's just a definition of what we're calling the trace, then it has the algebraic property of a trace. The trace of AB equals the trace of BA. It's not a trace in the usual sense. If you took any operator in the observer algebra and took its trace in the Hilbert space of states of the de Sitter space plus the observer, that trace would be infinite. This is a renormalized trace which is finite and well-defined. It's non-degenerate, meaning that for every A there's a B for which the trace is of AB is non-zero. We can simply take B to be A dagger. Yes?
You said you weren't going to go through the proof, but I was just wondering, do you use positivity of the observer energy in the argument?
No, I don't think so. That goes into the fact that the trace of the identity is finite. That goes into the fact that the trace is finite for all elements of the algebra. Okay, see, that goes into the fact that the state psi max is normalizable. Let's look at the definition of psi max. So psi max is normalizable because Q is bounded below. So if we don't have Q bounded below, everything will still be true except that psi max is unnormalizable, and therefore some operators will have an infinite matrix element in the state psi max. Not all. If you try hard, you'll find operators with finite expectation values, finite matrix elements, but the lower bound on Q made psi max normalizable, and therefore makes the expectations finite for all operators in the algebra. Well, that was the wave function. So the probability distribution is the square of the wave function. So now, well, let HDS be the Hilbert space we get by quantizing fields in de Sitter space. Well, I said it's important to just understand. Okay. I want to skip through this point quickly, but what I wrote was that it describes HDS perturbed by any number of gravitons, but not by a number of gravitons of order 1 over h bar. And therefore, it describes back reaction of an amount of order g, but not back reaction by an amount of order 1. Anyway, let psi be any state in this Hilbert space and consider the function that takes A to its expectation value in the state psi. Roughly speaking, because the observer algebra has a trace, we can hope that there's a density matrix in the algebra such that the expectation value of A in the state psi will be the trace of A times rho, just as in ordinary quantum mechanics. Well, is this true? Well, okay. Furthermore, we expect that, as in ordinary quantum mechanics, Rho will be a positive element of the algebra with trace equals 1. Positive will mean that it's positive as a Hilbert space operator. Well, I'll show you how to find what is rho for a dense set of states, and then we'll explain what to do to make it exist for all states. We could start by finding the density matrix of the state psi max. Well, the definition of the trace makes it clear that the density matrix of the state psi max is 1, because the condition we're supposed to satisfy is that for any a, the expectation value in psi max is supposed to be the trace of a times sigma max. But the definition of the trace of a times sigma max is that it's the expectation value of a times sigma max in the state psi max. So in other words, we're supposed to find sigma max such that this equals this. And obviously, the operator that does that is 1. So the density matrix of the state sigma max is the identity. That means that psi max is maximally mixed, similar to a maximally mixed state in ordinary quantum mechanics, whose density matrix is a multiple of the identity. In ordinary quantum mechanics, we don't usually normalize the trace so that the trace of the identity is 1. We usually normalize it so that the trace of the identity is the dimension of the Hilbert space. That's why in ordinary quantum mechanics, a maximally mixed state has a density matrix that's a multiple of the identity, but here we actually got the identity. The reason we chose this normalization of the trace that doesn't match what we do in ordinary quantum mechanics is that we didn't know what else to do. It was a renormalized trace in which we removed an infinite factor. And we didn't know how to pick that factor exactly, so we picked it to make the trace of the identity 1, because we couldn't think of what else to do. But in ordinary quantum mechanics, for a finite dimensional Hilbert space, you simply usually use the naive Hilbert space trace. But anyway, the state psi max, because of this, is the analog of a maximally mixed state in ordinary quantum mechanics. So I gave you the density matrix of one state. Now here are some more states. Take any operator in the observer algebra and let it act on psi max, and let's call that state psi a, and let's try to find its density matrix. Well, I claim the density matrix is a dagger. The property it's supposed to have is that for any b in the algebra, the expectation value of b in the state psi a is supposed to be the trace of b times the density matrix. But with this definition of psi a, this matrix element is equal to this. And by definition, that's the trace of a dagger ba. But because of the cyclic property of the trace, that's the same as the trace of b times a dagger. And that's the condition which tells us that a dagger is indeed the density matrix of the state psi sub a. And you can see that a dagger is a positive operator, as expected, for a density matrix. So we found the density matrices of a lot of states. And in fact, by essentially the Riesz-Leiter theorem of ordinary quantum field theory, these states are dense in Hilbert space. Incidentally, if they weren't dense in Hilbert space, the observer wouldn't care about the other states, right? So the states the observer can access, assuming the observer can access the state psi max, are these states and perhaps limits of them. But anything orthogonal to these states, if they existed, wouldn't be of interest to the observer. But anyway, these states are dense in the usual Hilbert space by essentially the Riesz-Leiter theorem. So we found that a dense set of states have density matrices. If we want all states to have the density matrices, we have to take an otherwise unnecessary further step. The Hilbert space HDS is the closure of the dense set of states A of psi ds. So if we want every state to have a density matrix, we have to similarly take a closure of the observer algebra. And this closure, which is no longer background independent, can be defined as the von Neumann algebra generated by bounded elements of the observer algebra. I'll call the closure, in this case, A observer comma ds, because we needed the choice of de Sitter space, or in general, some space-time the observer is living in, for it to make sense to take this closure. When we only had an operator product algebra, we wouldn't have known how to take this closure. But when we have a representation of the operator product algebra, we can take limits of operators. That's a meaningful notion. in the von Neumann algebra sense. We can take a closure. And then it's true that every state in the algebra has a density matrix in this closed algebra. It's this step and here only that we talk about von Neumann algebras, if we want to be able to make a statement about every state. Well, what is what I've told you useful for? Let's recall that Bekenstein and Hawking discovered that one should attribute an entropy to a black hole horizon, and not long afterwards, Gibbons and Hawking suggested one should also attribute an entropy to a cosmological horizon, such as the horizon experienced by an observer in de Sitter space. In fact, they gave that as the prototype of a cosmological horizon. So, in this case, the cosmological horizon, well, you would probably think of this future horizon. And an interesting cut of the future horizon is the intersection of the past and future horizon. And something I told you before is that in ordinary quantum field theory, there aren't any operators you can define on that cut. I'm just saying that now. It's not part. It doesn't fit well in what I'm telling you in the next few minutes. But I just wanted to make sure you appreciate why I stated that point earlier. If there were operators you could define in that cut, they would then be central in the sense that they'd commute with the green wedge and also the operators in the opposite wedge, because they'd be space-like separated from each. But there are no central operators because, as we computed, there's nothing we can define. Well, I didn't quite show that there's nothing you can define in codimension 2, but we learned that by slightly elaborating on what I told you. Anyway, going back to Gibbons and Hawking, they said that we should attribute an entropy to a cosmological horizon. But a microscopic interpretation of what is meant by the entropy of a cosmological horizon has been even more obscure than black hole entropy. For black hole entropy, we have examples where we can actually compute the states that explicitly describe the states that represent the entropy. For example, notably supersymmetric black holes and BPS states. And I think it's fair to say that not only there, but in many respects, we understand black hole entropy better than we understand the cosmological horizon. For example, there's a Ryu-Takenagi formula for black hole horizons, but it either doesn't have an analog or it isn't understood for cosmological horizons. However, we can now give at least a partial answer to this question of what's meant by the entropy of a cosmological horizon, at least for the case of de Sitter space. I say a partial answer because the notion of entropy I'll give you has an additive renormalization constant. Once we know every state of the observer algebra has a density matrix, we can define entropies. The usual definition of the von Neumann entropy of a density matrix is minus the trace of rho log rho, and that makes perfect sense here. And although I won't show it in this lecture, it's possible to show. So this gives a definition of entropy for any state of the observer algebra. And it's possible to show that that agrees with the usual generalized entropy up to an additive constant that's independent of the state. Because of that additive constant, I only claim this as a partial explanation of what entropy means. But we at least do have a natural explanation of entropy differences, how the entropy of the cosmological horizon changes if you change the state. The reason there was an additive renormalization is that the trace that we used was obtained by a multiplicative renormalization from a natural Hilbert space trace. If you follow through the steps, you'll see that a multiplicative renormalization of rho becomes an additive renormalization of the trace. Because when you rescale rho, you have to rescale the trace. Or I should say, if you rescale the trace, you'd have to rescale rho to keep its trace being 1. And that would shift the trace of rho log rho by a constant. So what we will define is really only entropy measured relative to the maximum possible entropy. Although at the end, I will offer a conjecture for a better definition. So in ordinary quantum mechanics, a maximally mixed state has a density matrix that's a multiple of the identity, and it has the maximum possible von Neumann entropy. The analog here is the state psi max, whose density matrix is 1. It's clear that its entropy is 0 because the log of 1 is 0. And by imitating an argument that in ordinary quantum mechanics, proves that a maximally mixed state has maximum possible entropy, you can prove that every other density matrix has less entropy. So the state psi max does have maximum entropy. That's why I called it psi max. One way to make the proof is as follows, although I'll go through this quickly, I'm afraid. Let ρ be any density matrix other than the identity. A convex linear combination of density matrices is still a density matrix because it's a positive matrix of trace 1. So ρ sub t defined this way is the density matrix if t is between 0 and 1. And then I let f of t be the entropy of ρ t. Gosh, I wrote, so as the entropy of ρ is f of 1. And then, although I didn't write it, f of 0 is 0. And it's fairly obvious that f prime of 0 is 0. And if you work a little harder, you can prove that f double prime of t is negative for all t between 0 and 1. To prove that, you do a little computation I've written here. I don't want to go through it carefully. But since f of 0 is 0, f prime of 0 is 0, and f double prime is negative, we learn that f of 1 is 0. So we prove that the entropy of any density matrix other than 1 is negative. So that proves that the state psi max does have maximum entropy. So the system consisting of an observer in a static patch in de Sitter space has a state of maximum entropy, which is simply empty de Sitter space with a thermal distribution of the observer energy. Well, why did this happen? The original argument that empty de Sitter space has maximum entropy goes back to 25 years ago by Busso, who argued that this must be true based on the second law of thermodynamics because the static patch is empty in the far future. Okay. I've drawn the de Sitter Penrose diagram again, but in Busso's discussion, the observer wasn't there, so ignore the fact that the left edge is labeled by the observer. And then anything which is in this static patch with probability 1 is not aimed perfectly at this point in the far future, so it will exit from the static patch through the future horizon. So in the far future, the static patch becomes empty. We can modify that slightly. We define the static patch by the presence of the observer. So for us, by definition, the observer doesn't leave the static patch. The static patch is the portion of space-time the observer can see. So although I didn't explicitly take into account in this lecture fluctuations in the observer orbit, the observer algebra is really the operators along the world line no matter how it fluctuates. So by definition, the algebra of interest, well, it's what the observer can see. Anyway, in our discussion, we don't worry about the observer leaving the static patch. But we can expect that in the far future, the static patch will be empty except for the presence of the observer, and the observer will be in thermal equilibrium with the bulk static fields. So in other words, in the far future, the system with the observer will evolve to the state psi max. Now, Busso said that, since the static patch spontaneously evolves to be empty, the second law is telling us it's evolving toward maximum entropy, so this empty de Sitter space must maximize the entropy. This statement was based purely on thermodynamic grounds with no microscopic definition of entropy. In today's discussion, we do have a microscopic definition of entropy, and we've justified the assertion that with this definition, the empty static patch with the observer in thermal equilibrium is the state of maximum entropy. So the maximum entropy state we found is the one you'd get by adapting the original argument to the presence of the observer. Now, in a more general space-time, I told you how to define the observer algebra in a universal way. But I don't know an equally explicit definition of entropy for an observer in a general space-time. I will, however, offer a conjecture, which is inspired by Aaron Wohl's proof of the generalized second law, and has a little bit of support by recent work of Chen and Pennington. So, Wohl proved a version of the generalized second law by interpreting generalized entropy as relative entropy of an arbitrary state with the Hartle-Hawking state of the black hole horizon. In cosmology, the analog of that would be the Hartle-Hawking no-boundary state. So, inspired by Wohl, I would suggest, well, first of all, various authors have suggested that the no-boundary state is in some sense a state of maximum entropy. And if that's the case, then actually, as in Wohl's work, and also as in ordinary quantum mechanics, entropy can be defined as relative entropy with a state of maximum entropy. So this suggests, if we interpret the Hartle-Hawking no boundary state, well, first of all, the Hartle-Hawking no boundary state is very poorly understood. In a general space-time, we really have no inkling of what it is concretely. I can't promise it exists. I certainly can't promise it's a state of maximum entropy. But if we're willing to believe that the no boundary state exists, then, and try to interpret it as a state of maximum entropy, then I can indeed give you a general definition of the entropy, of what entropy means in general for an observer interacting with the cosmological horizon. And there won't even be an arbitrary additive constant. I'll fix the additive constant in the definition of entropy. So the expectation value in the no boundary state of an operator is a state of the, assuming that the Hartle-Hawking no boundary state exists. It might be what in von Neumann algebra language is called a weight. It could be unnormalizable. So the assumption I'm giving does not assume the Hartle-Hawking state is normalizable, and I believe in most spacetimes it isn't. But anyway, the expectation value in the no boundary state of an operator in the observer algebra is a state, or possibly technically a weight, of the observer algebra that I'll denote as sigma. Then if A going to rho of A is any state of the observer algebra, I suggest that the relative entropy between rho and sigma gives a general definition, up to with a minus sign, of the entropy of a state seen by the observer. So this is my proposal for what entropy of an observer in any space-time interacting with the cosmological horizon means. Or there might be no cosmological horizon. You can argue kind of heuristically that if the observer can see the whole universe, this does agree with the standard definition of entropy. So that's actually another case where it works. But anyway, this is meant to be a general, the evidence is limited, but this is a proposal for a general definition of the entropy of a state of the observer algebra in any space-time interacting with cosmological horizons, or perhaps not. Yes, Andy? And then you?
Can you give an example of something that would be called a Hartle-Hawking state that is not distinct specific space?
Well, there are a few papers giving examples. But there's a fun example that some of the postdocs at the Institute have been looking at. I'm not sure how much I should say about it, because there isn't a paper yet. Okay. Well, yeah. There's limited knowledge. There's limited understanding of the Hartle-Hawking state. But the knowledge is so limited that I'd have to say the evidence for this conjecture is very meager. On the other hand, whatever is known about the Hartle-Hawking state, I think, is consistent with it. One thing I want to say is that in stating this conjecture, we do not try to normalize the Hartle-Hawking state. I did that in my paper, actually, the paper that has roughly the same title as today's lecture. But I think that was the wrong thing to do. We should take the Hartle-Hawking state as it comes actually from the path integral. And then relative entropy between, so rho will be a normalized state because the observer is studying probabilities. And for probabilities, rho has to be normalized. Sigma is whatever comes from the path integral. You see, the observer in one space-time wouldn't know how to try to normalize the no boundary state, because the normalization, if it is normalizable, the normalization integral is probably dominated by some other space-time that the observer doesn't know about. So physically, it's not well motivated. Even if you think the no boundary state is normalizable, it's not well motivated for the observer to try to normalize it. So relative entropy between a normalized density matrix rho and any density matrix sigma. Any density matrix means it's positive, but not necessarily with trace 1, is well defined and has no arbitrary constant. And in the case of de Sitter space, it gives the correct de Sitter entropy, A over 4g in the small g limit. So in my lecture, I had 0 for the maximum entropy state. But this definition actually gives A over 4g for the maximum entropy state. The only trouble is that, well, in the version I gave 5 minutes ago, I was making precise statements that I could justify. And this is more like a flight of fancy. I don't know if this statement is true. So a lot of things are missing. So somebody already asked me about an observer or civilization that didn't always exist, like us, for example. We didn't always exist in the past, and who knows about the future. And I use field theory language in this lecture. Can the discussion be generalized to string/M theory? So, so the definitions make sense whether or not there are black hole or cosmological horizons, but the discussion I've given is certainly more interesting for an observer who interacts with black hole and cosmological horizons. And of course, something which is missing is some more knowledge about the Hartle-Hawk, the no boundary state, which would enable us to say something, well, to either reject the conjecture I made at the end or to justify it better. Thank you.